All right, everybody, welcome back to another module of QTM 200, Applied Regression Analysis. In this week, we're going to talk about how to transform our variables as a means of overcoming some of the assumptions that may be violated, like we talked about in the previous module. And we're also going to talk about what to do when our covariates or predictors are related to each other. And just as a pleasant reminder, our overarching goal every single week is to take data that we get from a given sample and make an inference about a larger population. And last week we talked about how we can investigate whether outliers are impacting the estimates from our regression analysis. Now today what we're going to be talking about is how to transform variables, and specifically we're going to be talking about how to overcome issues of skewness in our covariate distributions as well as our outcome. We're going to talk about non-normality with regard to the distribution of x at a certain value, as well as non-constant variance, and we'll kind of talk about that in a couple of slides. And we're also going to talk about how to identify and correct for collinearity or covariance between our predictors in our regression. To start, I want to remind you what the key assumptions that we've made for linear regression are. The first being, one, linearity. We're running a linear regression, and what we mean specifically by that is that the population means of our outcome are going to have a straight line through them for different values of x. And that makes sense when you think about the fact that we're trying to fit a regression line, and that regression line is going to go through the center of each distribution at each given value of x. So you can see that happening here, right? So the mean for the distribution at x equals 0 would be around here. The mean for x equals 2 would be around here. And again, we're fitting the regression line through each conditional mean. Our second assumption is normality. And when we talk about normality, we're talking about, again, the population values of y for each value of x. It's going to have a normal distribution. And we can see that graphically here, right? Again, this is an assumption. So conditional on x equaling 0, the population values for x equals 0 should follow a normal distribution. Now, not only do we have to assume normality of that distribution, we have to assume constant variance. And so we're saying that the spread of that distribution is equal for each different value of x. So remember that these are assumptions, and these assumptions are often violated. And I want to go through a couple of examples to show you visually at least instances in which we may or may not think that these three assumptions are violated. And so let's just take a look here, and we'll walk through each answer and say why it is or is not likely. And so let's start with the first option. There is a linear relationship given by the data. So again, do we think that that is violated here? Again, the second assumption we have is that the population values of y conditioned for each of our x values follows a normal distribution. Do we think that assumption likely holds? And third, does the population value of each y conditioned on each x have the same standard deviation or the same variance at each value of x, or none of the above? Now I'll give you a second to think about this. Let's start off with the first one, and it does seem like the linear relationship is going through the conditional means for each value of x. It's a little difficult to tell, but it's unlikely that assumption is violated. Now, it's also difficult to tell whether or not they follow a normal distribution. What's more likely here is that we have unequal variance, and we can tell because we have very tight observations around the fitted line for lower values of x. But for larger values of x, the observations are much farther away from the fitted line. And so again, it's likely that B or C is violated here. We can also look at this example and go through the same checklist. And I want you again to think about which assumptions are likely to be violated. Now, let's take a second and think about it. And if we begin with the first assumption, I don't think that we would say that the fitted line does not go through the conditional means for each value of x. That seems like that is likely happening. It also seems like there is pretty uniform variance. So let's briefly review how we would go about checking whether or not these assumptions are actually holding, right? We can't just look at the data visually. We need to check mathematically and statistically on top of visually whether or not our assumptions are holding. So first, to check constant variance assumption of the errors, we can plot the residuals versus the fitted values. If you remember correctly from last module, we can get that by just doing plot with our LM object in R. We can also check the normality assumption with the QQ plot of the studentized residuals, again, hoping that they have a linear relationship going from the origin to the top right. Third, we can check for large leverage points by plotting H values, and then we can check for outliers just by running outlier test. Now, influential points would be a combination of having large leverage as well as large studentized residuals, and we can check that by looking at a bubble plot.